I want to wish you a happy Monday. It's a beautiful day, outside and inside, and all of those good things that go with it. We have got quite a few things to do today, so I want to make sure we have plenty of time to do them, which means that I'm going to start right now. I really don't want to talk over you. Please and thank you. I want to remind you, I think I've said this before, and if I haven't, I want to tell you now that I am taking some students to a Women in STEM conference on Friday. We still have a couple of seats in the van, so if you are interested, if you would like to join us, we would love to have you. Just talk to me and let me know today or tomorrow. Yes?
Wait, where's it at? Is that far away?
It is in...
How much school will I miss?
The whole day. And I said this to other people as well, because sometimes people are smart, Alex. I am not going to judge, and if you feel like it's an appropriate place for you to be, then I'm happy to take you. Does that make sense? Yeah, because I'm not going to assign you into any space that's not my role to do. So anyway, if anyone is interested, I would love to take you. I think it will be the full day. Great speakers and activities and things like that. It's in just north of Cedar Rapids, but I can't remember which suburb up there. I get confused. Anyway, if you want more information, let me know. All right, so I was looking at your homework over the weekend. I was like, ooh, there are a couple of things that maybe we haven't quite talked about. I feel like we got a little bit rushed at the end of the day on Friday. So I'm going to define a couple of things for you really quickly. So we'll do a little bit of notes. Then we're going to go over some homework. Then we're going to do some ranking tasks and problems. And then we're going to end the day with, I want to introduce you to the task that you will be asked to do tomorrow, okay? It's kind of a lab problem that you'll be working on, but I want to introduce it to you today, and that will be your homework for tonight. Make sense? Questions yet? Fantastic. All right. So 2 things that we need to talk about. One is the concept of a closed system, okay? This concept is fairly straightforward, but it is very, very important when it comes to physics. We said, and I'm going to back us up to last unit for a minute. We said that momentum, I know it's frozen, hold on just a second, is always conserved. We said that momentum is always conserved. And that's all well and good, and I kind of glossed over the like caveat that's important there. I didn't get out the carts, but let me just describe for you an example that would go counter to this. If I had one cart here, I'm going to call this cart B, and I had another cart here, and I call it cart A, and I push on cart A, and I watch just cart B in this situation, and I watch cart B. As cart A is coming, what is B doing? It's at rest. So tell me about its momentum.
0.
It's 0. After cart A hits it, then what happens to cart B? It accelerates. It's going to start moving, and its momentum is no longer what? 0. Is the momentum of cart B conserved?
Sure. That makes you happy.
It was 0 initially, and it is not 0 after. Does 0 equal not 0? No. Is the momentum of cart B conserved? No. But I said that momentum is always conserved. So there's lies happening. Lies. There's something that we're missing. What are we missing?
In a closed system.
Has to be in a closed system. In a closed system, momentum is always conserved. In this story, what's the closed system? Carts A and B together, right? A closed system is a system where there are no outside forces acting. So if you look just at cart B, are there any forces acting on B? Yeah, the force of A on B, right? Yeah, so that means it's not a closed system, but if we make the system both carts A and B together, are there any outside forces? No, there's an internal force. So we're assuming that we're not talking about, how do I want to put this? we can always fight about whether or not the Earth is part of your system, right?
Yeah.
And I don't want to get into that piece of it. In this case, we kind of are calling the Earth part of the system because it's pulling on them and the track and all of that. But the things that I'm really focused on are cards A and B, okay? And we're assuming no friction because, again, friction would be one of those outside forces that's causing trouble. Not trouble, literally, but causing that to not be true.
So
Go ahead.
In the closed system, you just look at the forces that like the objects make on each other.
So I want to make sure that I'm understanding the question you're asking. In a closed system,
Yeah.
let me say two things about it. Is that okay?
Yeah.
The first one is not what you said. The second one will be. Okay. So in a closed system, momentum is always the same. Linear momentum is.
Yeah.
So that means that the total momentum of this system, with whatever else you're including in it, will always stay the same, regardless of if it's before or after the collision. There are forces, right? They're internal forces. And the funny thing is that they're all Newton's third law pairs. Okay? So in these closed systems, the forces that you have are Newton's third law pairs because you have the force of A on B. But if you think about it, if you think about just a system of A, it has a force acting on it too, right? Its momentum by itself is not conserved because B acted on it. You with me there?
Yeah.
B accelerated or changed the motion of A in the same way, but the force of B on A and the force of A on B are a third law pair, okay? And that third law pair can be part of a closed system. So it's not that there aren't forces, but all of the third law pair forces are put into the box, okay? Isaac, did that answer the question you were asking?
Yeah.
Okay, all right. So that's in momentum. Now, we've talked about energy a little bit too. So momentum is always conserved in a closed system. Energy is also always conserved in a closed system. Sometimes you have to be a little bit careful about what your system is, what you're defining as being part of your system, okay? So we can talk about this with our frog. We can talk about this in any of these cases, okay? When we assume that there's no friction, and we're doing that for now, and then in a few days we'll bring friction into the story, okay? For now, we're assuming there's no friction because we don't want to talk about that outside frictional force that's acting on the system, okay? Once we bring that surface into our system, then we can talk about it, and that's totally fine as well. All right? So energy is always conserved in a closed system. So when we talk about the frog falling, what kind of forces are we talking about? What's acting on the frog?
Earth.
The earth, the force of the earth on the frog, right? The frog is being pulled by the earth. So really, what system are we talking about if we're saying that energy is always conserved? Earth and frog, it's one closed system, okay? As the frog pulls on the earth and the earth pulls on the frog, that's a Newton's third law pair now, okay? The gravitational potential energy changes, but the kinetic energy increases as well. That's why we can't just look at kinetic energy and ignore the earth, because if you just say that the frog speeds up, then its kinetic energy just gets bigger and bigger and bigger with no result, and then you wouldn't have conservation of energy. You wouldn't have energy being conserved. Does that kind of make sense? Okay. Isaac, is that a question, or that's just kind of a, you were like,
No.
okay, I just want to make sure I wasn't missing something. Okay. So that's the first one. I lied before when I said that we were going to do the two things and then talk about homework. I want to go to the question that's related to that in the homework real quick. Does that sound okay? And then we'll go back and do the other piece in a minute. So let's see here. I'm going to grab this homework. Paste it right in there. So question 11, I think, was the one. It says a diver leaps from a high platform, speeds up as she falls, and then slows to a stop in the water. How do you define the system so that the energy changes are all transformations internal to the isolated system? So here's the diving board, here's the water, here's the diver. have to be in order for energy to be conserved? What do we have to include? What objects? What things?
Water.
The water? Why the water?
That's where it's going to land.
Because that's where she's going to land. And not only is that where she's going to land, but what's going to happen? So she's going to increase kinetic energy, right? And then what's going to happen when she gets down here? She's got to stop moving, right?
Velocity is going to reach 0.
Her velocity is going to reach 0. So if we look at this, what kind of energy does she have up here? Just potential, right? Gravitational potential. What kind of energy does she have right here? Kinetic? Are we saying she has only kinetic energy there? Depends on which way you want to play the game, right? What happens here? What goes on here? She stopped. She slowed down. Where did all that energy go? What would we call that? I just mentioned it earlier. I said we're ignoring it, except just to kind of like, open up our minds a little bit. What applied a force to her? The water, right? What kind of a force was that? A frictional force? Yeah. So there, at this point, she's got no kinetic energy. We'll do more of these problems later. Does she have potential energy here?
Yes.
Potential.
Sure.
Potentially. Did you catch that one? That was funny.
That's really good.
Yeah.
Right?
Zero. Scarpling, what about buoyant force?
What'd you say?
Depending where the 0 or the H equals 0.
That's exactly right. It depends on where H equals 0. So I think if you wanted to set H equal to 0 here, you totally could.
Yeah.
Okay? And Jonathan might get mad. He might be like, no, I want to set equals 0 here. Doesn't matter. Because if you set H equals 0 here, then she's going to have potential energy down here. Does that make sense? Yeah. What are you unhappy about?
Nothing.
Okay.
How does she have potential energy down there if she's not?
Is it
Or
negative
if
potential?
I'm sorry.
It'd be negative.
Yeah,
Did that answer your question, or did you?
That's great.
So what? The water is part of the system. What else is part of the system? The diver. Anything else? Anything else applying a force to the diver?
Earth.
The Earth.
So buoyant force,
So the buoyant force is an internal force, right? If we include the water, because the water is applying a force to her and she's applying force to the water. Yeah.
Okay.
Yep. Does that make sense?
Yeah.
So yes, it's true, but that's part of the system. Yeah. Yeah.
the water on the ocean bed.
All right. How are we doing? Are we okay? Does that help to answer question 11 if you were stuck on it before? You're like, I don't know what that means. It's all about how big of a circle do you draw. Okay. All right. Questions about 28 or 29 from the homework? 29?
Yeah, we should do 29 and 51.
We're going to do 51, but I want to talk about something before we do that. So let's do 29 first. There's a lot of chitter chatter, friends. We've got a lot to do today. So if you have questions, please ask, or if you need to discuss, that's fine. But please stay focused on physics. Question 29. Oh, yes. So this one is similar to another one that we just ended Friday with. And like the bell rang as we were talking about it. But let's go through it real quick. A wrecking ball is suspended from a 5-meter long cable and it makes, bless you, a 30-degree angle with the vertical. The ball is released and swings down. What is the ball's speed at its lowest point? So I'm going to draw myself a wrecking ball. There it is there. This angle here is 30 degrees. This is very similar to the other one that we did last time, but let's just talk it through. It is a 5-meter long cable, which means that it's going to be 5 meters here. And when it falls, it's going to fall down so that it's hanging all the way down to 5 here. So it's going to go down as an arc of a circle. Does that make sense? It's not going to go straight over like that because then the string wouldn't be taut anymore. So it's going to come down here. So the wrecking ball will be down here. So this distance, I want blue, is also 5 meters. Okay. And it wants to know how fast, is that right? How fast will it be going when it gets down there? So we really need to figure out let me ask the question. What kind of energy does the ball have when it's here? It has gravitational potential, doesn't it? What kind of energy is it going to have when it's down here? Kinetic. Is it going to have potential?
No.
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 Well, yeah, it's gonna go up against.
No, that's where our H was here.
You just got to tell me, right? We're going to call this H equals 0. And if that's H equals 0, then all it's going to have when it's there is kinetic energy. So that's kinetic. And now I'm going to draw this nice little triangle here. Because, right, triangles are always a nice feature of existence, right? In this case, I've got a hypotenuse of 5. I've got an angle of 30, so I've got a 30, 60, 90 right triangle. Can you find the length or find how high up the ball is relative to its bottommost point? Can you find the pink part?
Yes.
Yeah. If you can find the pink part, the pink plus the yellow has to equal 5. You with me there? Is that cute, right? Pink plus yellow has to equal 5. So then you know the height. So this is MGH. And we know that the gravitational potential energy plus the kinetic energy at the top has to be equal to the gravitational potential energy plus the kinetic energy at the bottom. And you can use I and F or T and B or A and B or Q and I don't really care what letters you use. As long as you know that this is at one point and this is at the other point. Okay? At the top, we said that there's no kinetic energy. See you later. At the bottom, Isaac told us that it's H equals 0. So that means that there's no gravitational potential. So you've got MGH at the top equals 1/2 MV at the bottom squared. Did it bother anybody that they didn't tell us how big the wrecking ball was?
Yeah.
Yeah. But now should it?
No.
No. Because the mass goes bye-bye. See you later. Have a great day. So the mass goes away. And you can find then the velocity. Yeah.
But did you know the answer?
I don't off the top of my head.
So
Somebody get it? It's an odd, so we should be able to find it at the back of the book. I can look it
So,
up.
so this is the top height is the orange circle, right?
The height that it was at is yes. Does that make you happy or are you unhappy about that?
I don't know yet.
Okay.
Actually, it makes me unhappy.
It makes you unhappy. I don't want you to be unhappy. Chapter 10, question 29. Let's look it up here. Oh, wait, it doesn't have them, does it? Somebody get the answer?
I had 3.7. But
Do you guys agree?
okay, come on.
What was that?
She said 3.6 and I said 3.6.
Okay, so about 3.6, 3.65, something like that?
Yeah.
Okay. All right, can we keep cruising? Or not quite? So the height is literally just how high above H equals 0,
Yeah.
right?
The height is the 0.6.
Yeah, it's going to be a small number.
And then that's
Oh.
All right. I am going to start tiptoeing towards the next thing. Is that okay? Or not quite yet?
yes.
Oh, you want to do 28 too quick? Yeah. Yep. What?
If you're using like the 9.81 figure,
Indeed.
wouldn't h by 0, but h equals 0 by definition, you get like sea level.
So 9.81 is the average G. So, I mean, yes, but yeah, do you know what I'm saying? Like, yeah, it's all relative. Yeah, yeah. Okay, I'm gonna look at 28 real quick because there was a request for it. So it says a block slides down a smooth ramp starting from rest at a height h. When it reaches the bottom, it's moving at a speed v. It continues to slide up. Oh, I love this. A second smooth ramp. At what height is its speed equal to v over 2? I feel like we've done this problem before, and I don't mean that in like a why didn't you get it sort of way, but in a like these kind of all start to look the same. Okay? So a smooth ramp, it gets to the bottom, and it continues to slide up another smooth ramp. Something like this. Is that okay? So here's my box, and this is actually a very nice segue into the next thing we're going to do, so that's awesome. Okay? Starts from rest at a height of h. I'm assuming that means above the bottom. When it reaches the bottom, it is moving at a speed of v. And we want to know how high up it needs to be. Oops, there we go. H2, where V2 is equal to 1/2 of the velocity here. How do we do it? What's that?
I use the conservation of energy question, but I was just asking.
You totally should use conservation of energy. I don't know how else you do it. Yeah. Should we want to crunch through it and do it? Yeah? All right. I'm going to call these actually A, B, and C just so I don't get confused. So at A, what kind of energy do we have here? Just potential, right? At B, what kind of energy do we have? Just kinetic. And at C, what kind of energy do we have? Some of each, right? Yeah. So I think that we need to get this velocity in terms of this height, right? We need to get one in terms of the other. So I'm going to do the A and B stuff together. So we've got mgh at A is equal to 1/2 mvb squared. I'm going to call that VB down there. Okay. I think we'll need to do that so that we can get things in terms of h. The masses are going to cancel, and VB is going to be equal to, what is that going to be? That's the square root of 2gh. Does that look okay? I lost a 2. Now, I don't know that I actually needed to do that. Let's just keep going here, though. So, we want this velocity at C to be half of what it was here, right? What are we going to do next?
Solve.
Ding, 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 ding. What am I going to do to solve?
Gotcha.
What's that?
So you divide velocity is B by 2.
Divide velocity B by 2? Okay. And that's going to be equal to velocity c. Is that what you're saying? Okay. Then what are we going to do with that?
And use that velocity c to figure out what the potential energy is at.
Okay. So we got mgh at c plus 1/2 m times the square root of 2gh over 2 squared. Is that kind of what you mean?
Yeah.
Mm-hmm. And we need that in terms of the original height, right? So let's do that. So this is at C. Oops, let me erase that. Sorry, this is really yucky. This is all at C. Let's do that in terms of MGH at A, since that's the thing that we know it in terms of, right? There's a mass in everything. There's a mass in everything. What makes my life better? Get rid of the mass. Get rid of it. And this is H sub C also, isn't it? Or no, that's H sub A. That's the original height. Oh my gosh.
Whoa.
I don't know what that was about. It's like I slammed it so hard. It's like, oh yeah, oh no, for real? It's like, I'm done. I don't want to do this anymore. I quit. We're sorry. OneNote is cleaning up. Please hold. I mean, it's all there. It just needs to restart. It's okay. Maybe, maybe not. Wah, wah. That's awesome. Fantastico. All right. Maybe it's sending me a message. I'm going to come back to that problem when we can get it back. Is that okay? I'm going to restart, but I don't want to waste a bunch of time doing that right now because I don't know. I don't know why. Or click here. Click here. I want to click here.
The virus.
Oh, there it is. That was magic. It's just like so closest to being done with the problem. Is that what you meant? Or,
like it's virus.
yeah, or just click here. All right. Just got to read. All right. So it didn't want me to write an A. I'm going to try and write an A again. We'll see what happens. Okay. It was not writing the A. Okay. So we just need all that. We just need to solve for H sub C, right? I think. Let's do it. You guys doing this too, or are you just waiting for me? I don't know. So GHA minus 1/2. Actually, I'm going to simplify this stuff first. Holy cow, seriously? Okay. I think that my computer does not want to do this problem anymore. I am going to, let's see, where are we at? We're 2:30. Oh, we got lots of time. Okay, good. I'm going to teach you about energy diagrams on the board before the board dies, and then we'll come back to that problem. Is that okay? Is that okay?
Just write
Marker? I will. I would rather do it on here just because then I can record it, but if not, we'll see. All right, let's see if we can do this. All right. So the last question that you had to do on your homework was about an energy diagram because I thought we were going to get to it on Friday and then I didn't. So I want to do that really quickly right now. We did energy bar charts on Friday, but we didn't actually do energy diagrams. They're a little bit different, but they're pretty straightforward. So I want to do a couple right now. So this is notes again. Again, I apologize for my OneNote really just not wanting to do that problem. No, I will not. The technology is rising up. All right. I would like for you right now to draw a graph, like plotted graph, not a bar graph, of the potential energy of my frog over its distance as it falls. Are you ready? Here we go. It's going to do the same thing that it's done every other time when I've let it go. Just letting you know. I just want you to watch it because it's nice to watch sometimes. Here it goes. Whoa. What is that graph going to look like? Potential energy over distance. So your height or your position is going this way. Okay? Potential energy. No, I'm sorry. I lied. Kinetic energy. Do kinetic energy. I'm sorry, eraser. I apologize. I was getting ahead of myself. We'll do that one next.
Wait, position and relative.
Like
Height.
so
the ground is zero.
So like what position would be like closer to
0. Yes.
That would be the
All right. So this is position like relative to the ground. Okay. I want you to, so I hope that I'm making this really clear that I want you to graph kinetic energy. What happens to kinetic energy that falls? It increases. And what does the graph look like? What is it? A line? Is it a curve? Is it a curly Q? What does it do? What do you say?
It's like the parabol. Yes. Parabol.
Yeah? It's not over time, though. This is distance, right? So the reason I had in my head potential energy, it's mgh, right? As h gets bigger, what happens to potential energy? It gets bigger. As the potential energy goes up, what happens to the kinetic energy?
Goes down.
Goes down as the kinetic energy, as the potential energy goes down, what happens to kinetic energy? It goes up. It's a line, friends. Okay? It's a line. Because we're just talking about the energy.
But
Wouldn't it be from there, from the right?
It's like
Okay. Yes. Sorry. Yes. I misspoke. I'm trying to lead you from something that we understand to something weird and different, and I'm not doing a very good job of it because I got discombobulated with the question. So let me back up. I apologize, and I'm not presenting this in a concise way. Let me back up. I want to draw an energy diagram. I want you to have energy on this axis. I want you to have position on this axis. I want you to have a straight line here like this. Let me just say it that way. Okay? And I want to figure out what things are represented. That's really what I'm trying to go for. How does the total energy change? It doesn't. The total energy the whole gosh darn time is this amount. I write it as E sub T. I think your book just calls it E. Okay? That's the total energy. The total energy of the system does not change because it is constant because energy is conserved. Now, let's look at this again. And like I said, I may have presented it in a poor way at the beginning. I apologize for that. But I want to look at a few different points here. So let's call this X1, some position of the frog. Okay? And as that frog, let's see, how do I want to say this? I feel like I've confused myself and I apologize. As the frog is moving, this distance here is going to represent my potential energy. And if I have this much potential energy, how much kinetic energy must I have?
the reverse amount.
The whole darn rest, right? That's going to be my kinetic energy. What if I go to another spot like x equals 2 or x2? What happens to the potential energy? It goes up, up, up. And what happens to the kinetic energy? It goes down. I did present that poorly. I apologize. This would be an example of what? What are we doing in this to this object here? What's happening to it? It is.
Steve's
Right.
already.
Well, no, I mean, it is slowing down, right? It is slowing down. I feel like I'm writing this all backwards, but this is what they say. Yes, I just want to make sure that I'm doing it the same way that your book is saying it. What happens if I get here? It's all potential. Is it possible for that object to go above this green line that I have? Is it possible for my object to go over here?
Well,
Wouldn't it?
total energy would just be.
But in a closed system, is it possible?
Not in a closed.
Not in a closed system, it would not be possible. So I want to make that note because that's kind of important. In a closed system, an object's potential energy cannot be greater than its total energy. Not possible. Okay. The potential energy on an energy diagram is always the distance between the axis and the curve. Curve can be a straight line though, okay? The axis and the energy line, okay? And that total, like these pink lines can't go above the total energy. This energy diagram is not very interesting or pretty, let's be honest. Kind of boring. In your homework assignment and other places in the book, they give you more interesting energy diagrams. So I want to do one with you right now before we look at the one in the book, on your homework. Okay. So let me throw another one out at you that we can kind of look at what will be happening during this energy diagram. So let's say that we've got an energy diagram that looks like this. Okay. I don't know what it is that's causing that energy diagram. Obviously, it's not just a one uniform gravitational field, right? Like our other one was. Okay. I don't know what's causing it, but I can do some analysis as to what's going to happen. Okay. I can find the total amount of energy. It's going to be wherever it starts. That's the total amount of energy that this system is going to have. And generally, if they don't tell you otherwise, you're looking at that total energy being right here. Sometimes, though, they'll say, this is the energy graph, but you only have a certain amount of energy. And if that's the case, then you have to adjust where your E total line is. But generally, if it doesn't tell you, then we're just going to say the energy total is going to be wherever we start with. So at this point, if I call this x0 at the beginning, x equals 0, what kind of energy does that object have? All potential, right? We're going to call this a gravitational, system of some sort. If you give it just a little kick, where is it going to go?
Down.
It's going to go down, right? And as it goes down, so this is falling, right? As it goes down, tell me about its potential energy. It's going down. And what's happening with its kinetic energy? It's going to increase. And we can look at this and we can actually draw it out, kind of like we did with the other one. Let's do that real quick. So here's x1. And so I've got my potential energy here. And I've got my kinetic energy here. This is really, friends, just another way to look at the same stuff that we were talking about yesterday, or Friday, excuse me. Okay. And then if I mark some other points, we can ask some other questions. So this is x equals 2, and we'll call this x3, and x4, x5, x6. I've seen AP questions like this, which is why I want to make sure you've seen it. Where in this story will that object have the maximum velocity? X2. And what will it do when it gets to X2? Is it just going to stop, do you think?
No.
No, it's probably not just going to stop. So where's it going to go? It's going to go this way. It's going to slow down, right? Slows down. Is it going to stop up here? No, it's going to keep going. But as it does that, then it's going to speed up again. Does that make sense? And is it going to go all the way over here? It can't. Are you with me there? When I first learned about these, it looked just a whole lot like a roller coaster to me. Like, I can imagine riding on that roller coaster ride, right? And hold on one second. Let me just say this real quick, Henry, and then I'll answer your question. Is that fair? If you're a roller coaster fan, you have probably noticed that, assuming that there is no boost, because a lot of roller coasters now have a little boost that, like you'll be going and then it'll give you a little bit more of a chain or whatever. Can you have a roller coaster that does this if you start here? Is it possible?
Yeah. To make a roller coaster like that, but not to use it.
To ride on it. What's going to happen?
You're not going to make it all the way up the hill, silly.
How far are you going to get?
Probably halfway or less.
Right there.
Probably just where the other side is.
You will be, if there is no friction, you will get that high, right? That will be sad. And then what will you do if there is no friction? You'll just oscillate forever. If there is friction, what will happen?
You won't make it even more.
You won't make it this high. You'll probably make it this high. And then you'll come back, and will you go all the way back up here?
No.
No, you'll go to here, right? And back and forth and back and forth. Right? But you sure as heck won't go over here. Even if there is no friction. Unless there's a little bit of an extra chain that pulls you up. Sometimes that happens, right? Some roller coasters do have that. That's nice because that makes it more fun. But yeah, not going to happen if it's purely based on gravity once you get up to the top there. Okay. Questions on this? Did you have a question, Henry?
Yeah.
What's your question?
I'm confused. How do you find the total energy? Like, what is the total energy?
In what context? Are you talking about in this?
Yeah.
Unless it's otherwise defined, the total energy is the amount of energy you start with. So, like, I'm looking at this and I've got all potential, right? Now, if it says that I have a little extra kinetic there, I mean, like, I can't say it's always going to be this because there are lots of other initial conditions that may be true. Okay? But if nothing else is defined, then I would say that the total amount of energy is the amount of energy that you have in potential energy at the beginning. Does that sound okay?
Total amount of energy is the amount of potential energy you have at the beginning.
Yeah, in this kind of a situation. If you're not moving. If you're moving up there, then it's going to be a little bit more. Right? And then we'll bring like springs and frictions and stuff into that later, but we'll do that later. Not today. Are you happy or are you mad?
I'm confused. If it's where it starts, then why on the line graph was it at the top?
At the top.
So I don't do it.
Because that one, in this one, you mean?
Yeah.
Because in this one, this one I gave it some initial velocity, right? Because you were the one that told me that I was throwing this thing in the air, I think, weren't you?
Yeah.
Oh, okay. I thought you were. I interpreted it as you said that because you said that it was slowing down. Are you with me there? Yeah? So I'm throwing that frog in the air, which means that even though I don't have potential energy, I've got some kinetic energy come throwing it in the air. And that kinetic energy is slowly turning into potential energy, gravitational as I go.
So that was supposed to be when you were throwing it up?
Yes, I was mixed up with the way that I was describing it. I apologize. Totally my fault.
Alright.
My bad.
You're throwing the frog up and that's it, right?
Throwing the frog in the air. Yes. Yes. Yeah. I got myself mixed up. I apologize. That's
Okay.
totally my bad. All right. Really quickly. Holy cow. Really quickly. I just want to go through that homework question real quick. Oh, I can't. Silly thing. 51. Where was 51? Let's see. Oh, yeah. So 51 is very similar to the one we just did. Let's look at it, though.
Fancy.
Right? I know. All right. So in this picture, so we're talking about this one here, okay? It's a potential energy diagram for a 20-gram particle that is released from rest. From rest. From rest. Everybody caught that? That's
Yes.
from rest? Okay, good. Awesome. At x equals 1. So it's right
It's at rest.
at rest at 1. There. Okay? Will the particle move to the right or the left if it's given a little bit of a push? Which way is it going to go?
To the right.
It's going to go to the right because that's how it's going to speed up, right? It doesn't have enough energy. So if I draw here, this is where my energy total is, right? That's
Yeah.
because it says it's released from rest. So if I'm adding up my kinds of energy, I've got kinetic and potential. And at 1, I've got no kinetic energy, it's all potential. So that means that's where it's got to be. So 4 joules is my maximum amount of energy that I've got. Will the particle move to the right or the left? It'll move to the right because then it can gain kinetic energy as the potential energy goes down. What is the particle's maximum speed? How do you figure that out? Go, Jasmine.
The potential and kinetic energy should always add up to be 4 in this case.
Okay.
So the potential energy is mass times g times the distance or h plus 1/2 mv squared.
Okay.
That equals 4.
That has to equal 4.
Yeah.
That's fine.
But then you just plug in the values. So it was 20 grams, so it would be 0.02 times 9.8 times 3.
So where is it going to have its maximum kinetic energy?
At 4 meters.
At 4 meters, so right here, right? Mm-hmm. And so you're saying that H would be, you said 3 because it's 1, 2, 3?
Yeah, because if it starts from rest at 1, I was assuming it was at 4.
You're going to set that, okay. Sure. Yeah. I think you can do that. When I was looking at it, I was gonna make it even easier than that. But I'm not, talk to me here for just a second and check me and make sure this is making sense. This distance here is the kinetic energy, right? Or yeah, that's the kinetic energy. And so the kinetic energy's gotta be, what is that, 1, 2, 3 joules? So you can say that 1/2 mv squared
Yeah.
equals 3. And you know the mass? Solve for velocity? Is that okay?
Yeah, I mean, I did my way and I got like 1 off from the book, so I was wondering.
Yeah, I wonder if it's the distance thing. Yeah.
It is the distance. Oh, because you don't know for sure.
Yeah, that just seemed more straightforward to me, but either way I think is okay. And at what position does it have this speed? At 4 meters it has that speed? Where are the turning points of its motion?
Wait, I have a question.
Yo,
Which one is the B1 instead of part B1?
51 part B, I would do it this way. 1/2 mv squared is equal to 3. And then the turning points of the motion, this is something we hadn't defined yet. Here it's just speeding up and slowing down, but it's going to turn around there and there, right? When the potential energy reaches a maximum. That's when it's going to turn around. Holy cow, you guys.
Sorry, would you say for the second part B? I didn't hear you. I was trying to do the math.
You mean for part C?
No, part B too.
Oh, what position is this position? At 4? Does that work? Okay.
What was the
What's that?
Oh, at 6.
At 6 and at 1. Yeah. All right. We have 2 minutes. This is what I'm going to do. I'm going to introduce your lab tomorrow. I'm not going to worry about that today because that's too much to throw at your. I almost said at your heads. That didn't sound very kind.
You kind of are.
Is there any homework?
So I want you to try this problem real quick. Take a look up here. You got 2 minutes. Take a look at this problem real quick. Go, go, go. You got archers sitting on top of buildings. I don't know what the story is there. In each case, an arrow has been shot from the top of a building, either at 45 degrees up or down or horizontally out. All arrows are identical and are shot at the same speed. The heights of the buildings and the directions the arrows are given. Ignore air resistance. It says rank the speed of the arrows just before they hit the ground. Ooh. Give it a shot. Rank the speed of the arrows just before they hit the ground. Don't overthink it. That's the moral of that story.
No, they cannot all.
So it's equal C. Greater than A, which greater than B, which yeah, right. Jacob, right there.
Does that have anything to do with angle?
Just before.
No.
So how are we going to rank these?
Equals C is greater than A, is greater than B equals D.
Do you guys agree with them?
Oh, that's Rudy. That's fine.
Oh, do you agree with Rudy?
Yeah. See,
Harrison does. That's why he's saying it out loud. They're not all the same. We'll talk about it tomorrow.
Wait, how are they not the same? They're all shot at the same velocity.